Okay, thanks a lot. All right, so this is the title of the talk, which I considered to give some 2 years ago when I uh, sort of submitted this. But since then, quite a lot of time has passed, and there is perhaps necessity to refresh a bit the contents. So it's basically the same object which I was going to talk about, but the subject of the talk is the title of the talk is now different, and I think the subject is newer as compared to that one, although not unrelated. So the actual title of my talk is Fractional Shapiro Steps Without Fractional Josephson Effect. So let me make okay, so this is the work has been done in collaboration with Artem Galaktionov from Lebedev Institute and recently published in Physical Review B. Okay, so what is it about? It's well-known stuff I begin with. So it's we can consider superconducting weak link between two superconductors, BCS superconductors. And then basically, if one proceeds with theory, one can calculate the current phase relation, the supercurrent, across this weak link for any transmission values of all conducting channels that one has in this link. Now, it was pointed out long ago that if one considers subgap levels, subgap states, which are called Andreev levels, inside this weak link, then one basically, okay, this in the case of short weak link, you have two Andreev levels, two discrete levels inside this weak link, and this is a formula which defines the energy of these Andreev levels as a function of the phase difference across this weak link and the transmission channels, this Tn. And then it was pointed out, so this is a well-known fact, but it was pointed out that the current across this weak link, which I demonstrated on the previous slide, can also be calculated with aid of this simple formula, which basically tells you that you have to multiply the derivative of these energies of these Andreev levels with respect to the phase, multiplied by the filling factors of the same level, as you see here. And if you have, let's say, a Fermi distribution, you have which you always have in equilibrium, of course, then you reproduce just the same formula which I showed on the previous slide. Now, the situation becomes particularly simple, provided you have full transmissions, that transmissions of all conducting channels equal to 1. So you have fully open channels. Then the levels, the energy of these levels look like this as function of the phase, and they are defined by this particularly simple formula, which you see here. Okay, so far so good. Now, more recently, there has been a lot of activity related to superconducting junctions which include topological insulators. Okay, and for instance, here you see the picture of such a system that you have basically superconductors, in this case aluminum, which are connected to each other via some layer of via some topological insulator, and here you see this basically two-dimensional layer, and then it is widely believed that in such a system you have special kind of bound states which are called Majorana states. I'm not going to talk, I mean, I have no time to explain this in more detail, but I just want to say that I want to mention that the energy of such levels as function of the phase difference has exactly the same form as those of Andreev levels, which I showed on the previous slide, with the only difference that here we have a generally different parameter, which can be either equal to delta, and then it's just the same formula, or smaller than delta, depending on whether you have time reversal symmetry or in your system, in which case this delta small equals to delta large, to the order parameter of your superconductor, or a delta can be smaller, and as in this picture, provided the time reversal symmetry in your system is broken. Okay, so now the question is, what would be the Josephson current, the supercurrent in the system? Now, unfortunately, the status of this theory is such that nobody has calculated this directly, but people still want to get some idea what the current is. And so they use just the same formula as in the case of Andreev levels I showed you on one of the previous slides. What they do, they just substitute instead of this energies of Andreev levels, energies of Majorana states. Okay, take the derivative with respect to the phase and multiply by filling factors. All right, so if you do this, you get some expression for the contribution of this Majorana states to the supercurrent. And then it depends which filling factors you plug in. In the case of equilibrium, of course, it's Fermi functions, and then you get some expression which is similar to the standard one without Majorana states. However, people went forward with this, and they also assumed, and this is a crucial assumption, that this formula would work also out of equilibrium. That is, provided we drive the phase by applying phase in time, so it starts depending on time according to this formula, to this Josephson relation. If we apply a small voltage to the junction, yeah, and in this case, people assumed, and this is a crucial assumption, that actually this system can stay on one of the levels, making tours like this, and so the filling factor of one of the levels would be equal to 1 always, and of course then another level would be empty. In this case, this simple formula, so they plug this filling factor into this simple formula, and of course immediately get that kind of dependence of the Majorana contribution to the supercurrent as a function of the phase, which now depends on time. So it's time-dependent effect. That is what people sort of argue, and this actually has, this argumentation has the following major consequences. So if in the standard case we have the standard 2-pi periodic Josephson relation, here from this kind of argumentation we have unusual 4-pi current phase relation. Now, although it might look innocent to some of the people, in fact, it's not so innocent, because if you think a bit about this, you are bound to conclude that in this case, in the case you have 4-pi periodic dependence, the current is carried, current between two BCS superconductors, the supercurrent between two BCS superconductors is carried by single electrons with charge E, rather than by Cooper pair with charge 2e. And going to various conferences and listening to plenty of talks, mainly experimental ones on this subject, I always asked the question, how can it be? And unfortunately, none of the speakers whom I talked to, including basically the main figures in this subject, in this field, could not really answer this question. So this question remains open, at least to us, to the authors of this talk. Now, but in any case, another consequence, which is also quite significant, is that if we have this relation between the phase and the voltage, then we have usually we have of course Josephson oscillations with such a frequency in the case of 2 pi periodic dependence. Now here we have 4 pi periodic dependence, so we have half of the Josephson frequency. So we have, I mean, this people who argue in this direction, they predict that you have Josephson kind of oscillations, but with half Josephson frequency, okay? And then this means that if you also irradiate your system with external radiation, radio frequency radiation, for instance, then you are going to see fractional Shapiro steps, not integer Shapiro steps, but fractional Shapiro steps. And in fact, what people proceeded with such a systems and made such experiments, and in fact, they do see such fractional Shapiro steps, and they actually see that at small frequencies, you see, for instance, this plot here, this Shapiro step at the main Josephson frequency, 2e times v actually disappears here, and it reappears only at a higher frequency of external radiation, but at smaller frequencies. This is an important fact also. Okay, so and from this, people, these authors and also many others have concluded that they actually have an evidence for Majorana states inside their junctions. Okay, there is another experiment done in Grenoble group where people also see essentially the same kind of thing. They see this fractional Shapiro steps, but also they argued that actually the zero Shapiro steps, that is the Josephson current, without any voltage, just only in the presence of RF radiation, it actually doesn't go to zero, which they basically measured, they observed this. And this, according to them, could be interpreted as also as an evidence for this 5p contribution to the Josephson current, simply because in that case, you would see this picture that it doesn't disappear under, I mean, if you increase the power of your radiation, then this term would disappear here. This is a textbook result, but they see that they don't. This doesn't disappear, and then they explain it by the presence of this contribution. Okay. Okay. Now, so what's now I should come to the basically to the main subject of my talk. That is, I mean, in order to make some conclusions about the experimental results and interpret it this or that way, one should compare with the theory of Shapiro steps in the absence of Majorana kind of Majorana states inside of your junction. And this theory, although there were some contributions in the past, but up to now, this theory was lacking. Actually, complete theory was lacking. And the aim of our work is to construct this theory. And the key ingredient of this theory is, of course, the phenomenon which is well known, which is called multiple Andreev reflection. And this phenomenon is well, it's just this. So if you apply the voltage, then you have such kind of process which contributes to the current. So you have successive Andreev reflections here and here, and then you accelerate your quasi-particle, and then eventually it leaves the junction. And so even no matter how small your voltage which you apply is, the distribution function of your junction, inside your junction, becomes very sort of non-equilibrium. It has nothing to do with equilibrium form. For instance, I mean, you have this formula which tells you that it's not equilibrium function because of this process. And the result of this was actually shown first in this paper by Uwe Gunzenheimer and myself, which tells you that no matter how small the voltage is, if it is not zero, then you have this jump on the Ivy curve, which is directly related to this phenomenon of multiple Andreev reflection. So what can we learn from this? We can learn that basically you cannot just use kind of a diabatic approximation, which some people use, arguing that you can use this equilibrium formula for the current. So in fact, you cannot. And also actually, so this is the current voltage characteristic, the average value of the current. And here what you see is actually the current which depends on time, here in the limit of small voltages, which has this form. And this is a result obtained a year later by Averin and Vargas. And if you average with respect to time, then of course you get back this result. So so what you see here is that in addition to the standard ohmic term, you have this sort of excess current, which you see here, and it's by no means small. It's actually quite large, okay? And yeah, it has to do with this phenomenon of multiple Andreev reflection. Now in this, let me repeat again, that in this sort of naive description of Majorana state contribution to the current, this contribution was totally ignored. It was lacking, and so we see a bit of a problem at this point. Okay, so if you proceed with the calculation, I'm not going to go into details. It's basically Keldysh machinery, effective action, and stuff like this. You have here green functions and so on, and then you can calculate the current and actually all other cumulants. So I immediately, I mean, I have no time to discuss the theoretical part of our talk. I immediately come to the results. So first of all, let us recall this result for the supercurrent, this n equal to 0 Shapiro step, so to speak. That is, we consider the situation when the voltage applied has this form, this harmonic form, and no constant contribution to voltage. Then the phase across your junction has this form, and this is an important parameter which controls the strength of this applied AC field. Okay. Now, if you restrict yourself with such frequency, which should be smaller than this distance between Andreev levels, then you can easily reconstruct the result, which has this form. This is just a supercurrent equilibrium, supercurrent as a function of this phase. And in addition, you have this term, which perhaps I don't comment. This is sort of renormalized capacitance, which depends on the average phase. But in any case, if you average the result with respect to time, then you get this kind of expression, and which you can sum under this condition. You can sum exactly, but otherwise you just proceed to numerics. And here I just collected some current phase relations at different values of this parameter alpha, which controls the strength of AC radiation, the power of RC radiation. And then you see how it evolves if we increase this parameter. So the current phase relation is actually quite interesting to follow this evolution of this current phase relation. But basically, so I mean, you can look at this. But basically, if you look at the critical current as a function of this parameter alpha, then you see this picture. So each time it reaches the minimum, the junction switches from 0 junction to pi junction regime, and here again to zero junction regime. And if you follow this current phase relation, you can see this explicitly. Okay, but the important thing, it doesn't go to zero at any point, at any power of this radiation, which is what which was seen by Grenoble people. But let me emphasize that here we do not have any Majorana states. And this observation that the current doesn't go to zero, the supercurrent doesn't go to zero, is a simple consequence of non-sinusoidal current phase relation which you have in your system. Okay, and now we come to Shapiro steps. So we apply now AC voltage, radio frequency radiation, and you have also, we also apply constant part of the voltage. So the voltage has this form, and then of course you integrate, you have the phase in that form. And then what actually, if you study Shapiro steps, and this was done to a certain extent by these people, Averin and Bardas, our paper with Gunzenheimer, and also by Cuevas, then you see that under this condition, you have Shapiro steps at your current voltage characteristics. That is, you have resonances at your current voltage characteristics, where this K and N are integer numbers. Now K just follows from non-sinusoidal current phase relation. It is just harmonics. It describes harmonics of higher harmonics of the current, Josephson current, and the parameter N, as long as N is bigger than 1, describes multi-photon processes. So now this is well known. However, there was no complete theory. You know, the positions of these steps are well known, and now we proceed with this theory. And if we apply perturbation theory, then basically multi-photon processes can be ignored. So alpha is much smaller than 1. And then you have only integer Shapiro steps. Now, already this perturbation theory gets quite complicated, so I only quickly flash this these results for this integer steps for different temperatures and different frequencies and so on. But here we can learn something, but this I will leave aside. Rather, I will turn to non-perturbative results. So if we now have this parameter alpha not small, then basically we already get fractional Shapiro steps, and this K and N can have any value in principle, and the result looks, the general result for the current looks like this. But rather, I simply plot this Shapiro steps, this principal Josephson Shapiro steps, yeah, and this is first fractional Shapiro steps and the second fractional Shapiro step, and so on. So for alphas much smaller than 1, we have this simple dependence, which is illustrated here. So indeed, it's only main Shapiro steps, integer Shapiro steps, which matters. However, if alpha becomes of order 1, what we see here, for instance, then you see that actually this fractional Shapiro step, or this 1/2, can dominate in this frequency domain at least over the main Shapiro step, and so the same can be said about this step, and so on and so on. Okay, so basically the conclusion out of this is that this theory, which we now have, this complete theory of Shapiro steps in such kind of junctions, gives exactly the same results as people observe in experiments claiming Majorana kind of effects. Yeah, so here in our model, there is no Majorana states from the very beginning. We simply didn't include any physics like this. So it's topologically trivial Josephson junctions, which we consider. And what we see, I mean, I just collected the main results which we obtained here. And if you compare with this experimental graph, you see that it basically fits one-to-one to this picture. In particular, if you turn it by 90 degrees, then you will see that it's exactly the same. And then finally, this is about the last slide, is that approximately at the same time we did this paper, there appeared the experimental paper where people observed missing Shapiro steps, also in topologically trivial Josephson junctions, which strongly support this experiment, strongly support our arguments. So let me come to my conclusion. So we basically completed microscopic theory of Shapiro steps in topologically trivial superconducting weak links with high transmissions, and we basically obtain exactly the same features as people observe in experiment. This non-vanishing n equal to 0 Shapiro steps and fractional Shapiro steps, effect of missing Shapiro steps. And so we conclude that these theoretical results really call for reinterpretation of these recent experiments with topological junctions. Thank you for your attention.
Thank you very much, Andrei, for your very comprehensive talk, which probably doesn't make happy some experimentalists, but this is like it is.
Yeah.
And of course, a very correct approach. And now, if are there any questions over there, please?
Do you account the ratio between inelastic scattering length to the contact dimension in your approach?
Well, you see, we can, I mean, we have short junctions. We have considered short junctions. Yeah, so the inelastic scattering length doesn't matter here, but the inelastic rate we do have in our calculation, although it should be small at low temperatures, because there is no real mechanism which produces these inelastic effects. I mean, inelastic electron scattering at such low temperatures. So that's basically the answer.
As I know, there are papers in which people include fractional Josephson term directed to phase dynamics equations. In this case, as I know, no problem with Shapiro steps in Josephson junction with fractional term. In your case, from your results may be related with direct Andrei reflection. Inclusion of consideration of Andrei reflection effects in this junction. This is right or no?
Well, I'm not sure I understand your question actually. So can you condense it to, let's say, to one sentence or two, maybe, because I mean I'm not able to answer. I don't understand it.
The question is this one. As I know, there are any papers in which direct inclusion of fractional term to Josephson dynamics equation leads to presence of Shapiro steps. In this case,
okay, sorry. I mean, I probably know which papers you mean, but this is done by hand. You see, I mean, this term follows from nothing except for I mean. This kind of hand-waving arguments which I flashed in the beginning of my talk. You see, so if you make it by hand, then of course you have no problem. But the question how you derive it, I mean, that's the point.